This is my favorite subject, and I really appreciate having an opportunity to come here and talk about it. How many people in the room are groundwater research people? Just a few? And how many people don't really know what groundwater is? Okay, good. We've made a lot of progress there. I want to talk about this mapping effort in the context of culture first. Because as an applied science person, I come from geology into urban design and landscape planning. And as an applied person, I realize how the story has to work for people. So I use this example of the Minotaur. Most people are probably familiar with the Greek myth of the Minotaur, who is the monster living under the palace at Knossos in the labyrinth. And they would send a tribute of young people to the monster every year. The most beautiful, the most healthy young people were sent to be eaten by the monster every year. I think this is comparable to taxes we pay to maintain infrastructure. The monster underground, selling our children's future, trying to make this all work. So I think that's an interesting story about what's scary underground monsters. There are, as it turns out, a lot of stories about underground and underwater monsters. This one is H.P. Lovecraft's Cthulhu, mythic god, creature. Since Lovecraft was living in Providence, Rhode Island at the time that he wrote it, I imagine this like right in Providence Harbor there, this monster, waiting to change the city by its behavior. And then the classics are Paris catacombs, how frightening it is to think about associating the underground with death. We have a lot of myths and stories about this underground thing. And in cities, we live on sometimes a very thick crust and sometimes a very thin crust of infrastructure. This is an illustration by David Macaulay, a book called Underground for Children. Still one of the best resources for explaining to students what's underneath the pavement. And it imagines a view of the street as if the pavement has been peeled away. So this is all what's underneath that van on the street. And that complex crust of material could be only 8 feet deep in some relatively recently developed urban area, or under a city like Manhattan, it could be hundreds of feet deep. So as we talk about what's happening underground with sea level rise, it's difficult to realize how much legacy capital investment is in that crust and how much of it is at risk. For example, in New York, when they have a big hurricane coming, their new adaptation strategy now is to have a schedule of who has to run into the tunnels under New York City and pull out all the electronics before the water comes in. So that's how part of how New York is adapting is to pull all the delicates out of the tunnels before the water comes because they can't stop the water. And then this underground world of natural processes like this sinkhole that appeared in Guatemala City in 2010 triggers all those stories and fears of the monster underground. And what I think is really valuable about tapping into those stories is helping people both on the one hand to gain a new anxiety about what's underground and at the same time think about how to manage that anxiety and how to turn it into something that we can live with in a positive way. So I have a couple slides here on what is groundwater, just in case anybody wasn't sure. I always tell my students it's that stuff at the beach when you dig down in a hole and there's fresh water right there above the salt water on its way to the ocean. That's the freshwater water table. And that's what I'm interested in, is mostly the freshwater water table. And it's also called the saturated zone because it's that zone between all the soil particles in the ground, unconfined by any bedrock layers, where the pores between the soil particles are all filled with water. So it can easily be higher or lower depending on how much rain and infiltration into the soil is occurring. Rising groundwater is a new problem. It's one that we haven't thought of before. And that's maybe reasonable when you think that we haven't really had cities during a period of rapid sea level rise in the past. The last time there was a rapid period of global sea level rise was somewhere more than 8,000 years ago, and cities are between 5,000 and 7,000 years old. So we really haven't been through this before. We haven't had to manage cities through this process. But boy, do we have to do it now. This early paper in 2013 by Holly Michael at University of Delaware pointed out to a lot of people that there are a number of problems associated with sea level rise and with groundwater. One of those problems is that this submarine groundwater discharge will be limited by a rising water table, and that water table, as the sea level comes up, the water table will also rise. And then in some cases, the saline boundary will also rise. So we may see salinization in some places, and we may see just a rise in the freshwater water table in the other condition. And she's categorized the coasts of the world thinking about this and is calling that top condition a recharge limited water table condition, and this one a topographically limited, topography limited groundwater condition. Because what's happening is the groundwater is coming up to the surface and discharging through streams and springs. So it's really topography that sets the limit on where the water table can be. It's basically going to emerge, and in this case, there's still enough sediment on top of whatever kind that there's a zone where rainwater can still infiltrate, which is what we call recharge. This paper from 2012 is I believe the first. It was a USGS study to look at an urban area in terms of sea level rise and groundwater. And what they did with these contour lines, well, they did a three-dimensional model with a software tool called ModFlow of where the water table is. And then they simulated raising the sea level, this line here, by 3 feet. And these contour lines show where how much higher the water table would be. It's the difference between today and what it might be at with 3 feet of sea level rise. And this map allows you to see that there's a gradient of that effect going inland, but that in their study they found that that inland extent of the effect would go much farther than others have thought. We had thought about half a mile. And in this study, they discovered that it was reasonable to think it might be almost 2 3/4 miles, that effect would extend inland. And then they looked at raising the water table and adding about 12% more recharge, probably from rain, but we also get recharge from things like leaky drinking water pipes. So there is more than one source for what we call recharge. And in that case, you can see that same 3-foot line is back here, and what that means is the effect has extended, it's higher back here than it otherwise would have been. It's steepened the dome of that rising water table to have more recharge as well. And I don't know how many of you are following precipitation records for the East Coast, but the Northeast does have higher precipitation now than it did 20 years ago. So in effect, we are seeing an increase in recharge. And the way they look at that with real data, the USGS collected well data, groundwater well data, between 2009 and 2010 and connected the discharge of a surface stream in the red line to the elevation of that water table in the blue line. So you can see that as the water table goes higher, the discharge increases. I think of explaining that like my daughter over Thanksgiving had this pile of potatoes and there's gravy and an island in the middle the way she likes it, and then she plays with it and breaks the dam and lets the gravy drain out. Well, that's what's happening as the water table rises. As it intersects with a surface water channel, the gravy drains out. So the water table is adding to discharge when it intersects a spring or a stream channel. In Hawaii, at the University of Hawaii, Chip Fletcher and his graduate students and postdocs are representing the problem this way. They use this very kind of simple cartoon to show that they expect that groundwater inundation will occur inland as the sea level rises. That there'll be some percentage of the flooding that's marine, saltwater, and then some of this is going to be freshwater, groundwater coming up. And that because there are different viscosities, the freshwater is lighter, that it rises on top of the saltwater without mixing very much. And their paper in 2012, Rotzal and Fletcher, used a similar figure to explain the Hawaiian geologic condition on Oahu, and then used these two maps to make the point to policymakers. This one shows in blue where flooding would occur in downtown Honolulu with 1 meter or about 3 feet of sea level rise. And this one shows where flooding would occur in downtown Honolulu in various shades of blue to represent 1 meter of sea level rise plus what they know about the groundwater. So that's about twice as much area. And this is the area where Honolulu is building a light rail system right now and planning high-density transit-oriented development in a lot of those blue zones. So this matters immediately to policy if this is what we can expect. We have been looking at East Oakland, and I'll show you more about that in a few minutes, but we expect that in East Oakland, 25% more land may flood based on this relationship between salt water rising and freshwater rising. And we've realized, looking at heterogeneous urban conditions, that there are a number of other things to be concerned about, as if we didn't have enough things to be concerned about. One of them is that our sewer pipes are mostly cracked in a seismically active region without a lot of capital replacement and maintenance. So they will be infiltrated by a rising water table, and most of their capacity eventually will be taken up by that groundwater. So when people go to flush the toilet and use their plumbing, eventually it's not going to go anywhere because the pipe in the street will be full. The other problem is basements. Not everybody has a basement. I have a basement. I heard somebody say, nobody in the Bay Area has a basement. Wait a minute, I have a basement. And every winter I see water come up through the cracks in my basement after the rain. And I expect that to be the water table. So there are basements that may not only flood but also heave as that hydrostatic pressure gets strong enough. And that's what happens in cities like New Orleans. There has to be a foundation for your foundation. There have to be pilings under even things like concrete surface water channels to hold them in place by friction. So that's interesting to think about. How do you adapt to that? And then there are hazardous materials that are legacies from industrial sites, gas stations, and leaky underground storage tanks that our strategy has been to cap from above, but not to line from below. So those legacy soil contaminants could be remobilized if that water table rises enough to intersect those contaminated soils and start moving them around. And that means that that basement could face some serious problems. I'll talk about in just a sec. But this levee in the section is also important to watch as I show the water table coming up, because you can see it has no effect on what's happening behind it. And yet this levee, this kind of levee, is being shown in every drawing of residential development around the Bay Area that's being designed for the shoreline. Treasure Island, Mission Bay, Brooklyn Basin in Oakland. Those are all being designed, Hunters Point, with a levee, but no one ever shows you that you have to have a pump with that levee. Otherwise, your groundwater table will come up and flood the area behind the levee. Levees come with pumps. The Dutch know this. That's where the windmill was really useful. But American designers seem to have still had to discover this. The other problem is that as these contaminants are remobilized, basements are affected, even sewer pipes, some of these contaminants have a volatile organic component which can penetrate, that vapor component can penetrate pipes and cracked basements. And so without my ever having had to have contact with benzene floating on the groundwater surface, the volatile organic component of that benzene could come into my house, and that's in fact how most people are exposed to cancer-causing chemicals from the water table. So as the water table rises, liquefaction risks often rise also, depending on the materials. If you're in fill and the water table rises, the liquefaction risk is likely to rise. If you're on sand and the water table rises, it probably won't have that much effect on the potential shaking in a seismic event. But as we all know, we live in a region of faults. This entire center area is subject to some subsidence. And many parts of the Bay Area, here's the island of Alameda and the city of Oakland with Lake Merritt, have already got very high liquefaction probabilities because they're on fill over old wetlands. This is where the old wetlands come back and have their revenge. These areas are going to shake more extremely. This is a sandy area in the middle. And when they shake more extremely, we're going to see phenomena like this, which happened in Christchurch, New Zealand. The sandy soils along a river turned liquid, behaved like a liquid during a seismic event in 2010, I think it was. And this car dropped in while it was behaving like a liquid, and then Seconds later, it solidified and the car had to be dug out. So you can see why that's a problem for building foundations and for infrastructure buried in the street. Things pop up and drop down when the soil doesn't behave the way it normally does. And then we have a problem of subsidence. Roland Bergman's group here at Cal released these data earlier this year, and they showed in the red areas that have relatively high subsidence rates, around 4 millimeters per year here in the Bay Area. And so this area around Hayward is obviously a hot spot. There are a few others at the Bay Farm Island tip of the Oakland airport, for example. For some reason, Berkeley is subsiding faster than Oakland. I'd like to know why that is. Why did I buy a house in Berkeley? I should have bought a house in Oakland. And this subsidence can be accelerated by pumping. So that's the New Orleans story, that as people in New Orleans pumped old wetland soils, those soils collapsed. They were held in position by the amount of water content they had, and when the water was taken out, that platy clay material just dropped right down, lost 6 to 8 feet of volume. So as we look at the Bay Area and think about subsidence, San Jose, downtown San Jose dropped about 12, 15 feet because of agricultural withdrawals from the water table down there. And that was when they first built the very first levees in the Bay Area to protect downtown San Jose from the bay moving in its direction very dramatically. So those levees are there to protect that, and we have to pump drinking water into the ground in San Jose to keep it from sinking any further. We did a study of what would happen, doctoral student and I, if we chose different boundaries of the bay for that levee that I showed you. Basically, if we raised whatever protections exist now around the edge of the bay, only to the point we'd need to raise them to prevent overtopping, to prevent the bay from going over. So it's keyed into the actual topographic conditions and hydrodynamic conditions at each location around the bay. And if we chose what we were recommending was option B, this red line here in the middle, which is only slightly more expensive to protect us from 3 feet of sea level rise at $57 billion than the shortest possible line would be. We would get a fair amount of space, but that doesn't include the costs of the pumping. Of course, that could be done with renewable energy, but we'd still have the problems of how we organize that pumping. And whenever you install pumps, you create a choke point, where if you have excessive rainfall at a time when the pumps are already working at a maximum to remove groundwater, you would have freshwater flooding on the inland side of the levees anyway, because every pump has a limited capacity. So once you set up that system, you set yourself up for other kinds of vulnerabilities. I wanted to share with people an example of where groundwater flooding is evident already in the Bay Area. We can look at the tide gate for Lake Merritt right down here at 7th Street. And in a king tide, this is what that looks like. It's got a high water level. These are the tide gates embedded underneath the street here. And there are 2 pedestrian tunnels, one on either side. I'm going to show you a short video if this works. Apologizing ahead for my cinematography. That's the bay coming in through a crack between these barriers. Now we're looking up to a stairway that comes down from 7th Street. I know I'm making people dizzy. Here's the groundwater coming out of the hillside, and here's the groundwater coming up from below through those expansion joints in the concrete. So our infrastructure is not ready for this. We're going to see leaking happening from all over the place. And our question was, looking at this data mapping question, was where else is the groundwater high in the Bay Area? And we tried to figure that out. We found that the state has created a fabulous data set for us, not for this purpose, where they're tracking groundwater water quality, chemical data. So these dots all represent wells where they're also tracking the elevation of the water table, and they happen to be clustered in areas where there's more contamination in the soil, because that's the purpose of the data set, is to track contamination in the soil. So there's much fewer data points up in the North Bay in more agricultural areas. We looked at those data points to generate an interpolated surface, and we chose the highest elevation of the water table over 20 years. So am I making a worst case? Oh yes, I'm making a worst case. And I'm making it because it may just take one event in which the water table intersects with a contaminated soil area to cause a serious health exposure. So I'm not saying this is where, when I show you this surface, I'm not showing there's going to be emergent flooding everywhere around here. We also added the mean tide datum points that we had along the shore to tie that interpolated surface into the known tide level of the bay, the mean tide level, which of course is what will be rising. And we looked at all of those well data points in relation to a zero datum and in relation to the land surface. We found that a radial basis function was the best fit using a simple least squares error analysis. And so we used that radial basis function to generate a surface that reflects depth to the water table. And when we
difference between the water table and the depth to water and the saturated zone.
You may know more about that than I do. I use the
So we go back
yes.
to the previous slide. You have the dashed blue line, and then the saturated zone seems to be lower than that.
I meant the zone in between. Sorry, that used to be a bracket, and it referred to this whole zone, everything below that line, as the saturated zone. Sorry, I changed the graphics, and thank you for pointing that out. The saturated zone would be everything below this blue dashed line. Okay, back to the news. So all of these areas that are red are within 0 to 1 meters of the surface. That's where that water table at a maximum over the last 20 years is very shallow. That means it's already interfering with the function of storm sewers and sanitary sewers. And then these yellow and the orange areas are 1 to 2 meters, and the yellow areas are 2 to 3 meters. And these hatched areas are areas that are more than 1 kilometer from a well data point, at which point we lost all confidence in our interpolated surface. So we have a constrained data set. We're only 1 kilometer from the coast and 1 kilometer from a data point. So these areas are too far from a data point, and these areas that are white are too far from the coast. But you can see the Oakland Coliseum right here is surrounded by some high water table areas and some weirdness in terms of urban heterogeneity, where on the upland side of some major roads here, this is 880 and this is San Leandro Street, we see some what looks like almost ponding. And we don't know if those areas are what we might call perched up here and wouldn't be elevated more by the rising sea level because they're already elevated and they're just having a hard time getting out past the compacted soils underneath a roadbed. So the urban heterogeneity of compacted soils is going to be a big confounding problem in understanding how to model the rise of this. But this is empirical data, so we know where it's high now. We just don't know yet how sea level rise is going to raise this whole surface. And what everyone has been doing is looking at it in a very simplistic way, which I'll show you in just a second. This is El Viso, the El Viso area down by San Jose. Very high groundwater already. And these white zones reflect areas where there's pumping happening because of old contamination and a need to protect some underground infrastructure, some leachate collection infrastructure around a landfill. This one is East Palo Alto Mountain View. You can see there's a very high water table throughout East Palo Alto. In fact, they have a pump station right there where they're pumping continuously, even in the dry season, because they have such a high water table all year round in East Palo Alto. And that contributes to their flooding problems there. And this is San Rafael, which should be the poster child for groundwater problems, because the city already was under threat from the saltwater flooding. It's very, very flat, and these data reveal how close that water table is to the surface in that area. So that's a really tough spot. The black, I haven't really mentioned, those are areas where our interpolated surface intersected with the ground surface. And of course, you can't have the groundwater above the surface, so we're showing it black to call it to everyone's attention. Those are areas where the water table probably would be emergent at the surface if it weren't discharging. Picture that gravy lake on the mashed potatoes again. It's probably discharging from those black zones, so it doesn't reach the surface, but it's very close to it. Coming back to this map, we looked at just blue areas here, all these light blue areas would be emergent as sea level rises if the gravy doesn't run off the potatoes. So those would be ponds as we get 3 feet of sea level rise. All of those areas would be ponds if they're topographically contained enough to hold the water. And this is an example of a close-up of that map from Foster City, where you can see many, many sections of that landscape will be affected by an emergent water table. So the question comes up, how do people deal with a high water table in other places? I want to get to the good news, which is that there's something we can do about this. And since I work in an applied field, I wouldn't otherwise have much to say. So this is an important piece to me. The Dutch have done so many things because they live below sea level. And they spend money. They spend a lot of money. They spend 2% of GDP every year to try to deal with flooding. For the state of California alone, that'd be about $52 billion a year if we tried to match the Dutch investment in adaptation monies, flood management. This particular project is in a high water table zone outside Rotterdam. They built some high-end new housing. Well, first they dug out a pond in that high water table, and then they mounded some of the soil back up, and they put high-end luxury housing on the mounded earth, and they sold it to rich people, and it functions as a stormwater wet pond for the rest of that area, holding stormwater. This is infrastructure that they sold houses to rich people in. I am so down with that. Because that is the ultimate strategy for making money off of building a public benefit, making money back for the public by creating this land and preparing it. And then it is also the ultimate monitoring system. What are they going to do when they see a little leak happening? They're going to call the mayor's office, not just Public Works. So this is going to be very well monitored. This pond allows for another 2 or 3 feet of stormwater to raise the surface elevation, and if there's any change happening to the edge of that levee, I'm sure that somebody's going to make a call. So that seems like a very sophisticated alignment of interests to me. This is what the other side of that levee looks like, a more contemporary architecture. We would have a harder time building, frankly, just because we are not as contemporary in our tastes in many American housing developments, but maybe we'll see it in the South Bay, in the tech community. And then I want to show you one more, which is near Amsterdam. Of course, this image itself reveals the oldest way of dealing with groundwater in a city, which is to dig canals, create some positive pressure in those canals with a windmill, and then wick all that groundwater out of the blocks between the canals. The canals in the 17th century had to be spaced about 150 feet apart, about the depth of what a Dutch double block is, to drain that water out. So that was the original purpose of the canals, in addition to creating transportation routes for boats throughout the city. Now the Dutch are developing this part of Amsterdam, and this is all on a freshwater lake. And these are all floating structures in the center here, attached to fixed walkways. And these are conventional structures on conventional foundations, and this bar building is also on a conventional foundation, and people access the houses on the water from this end coming through the bar building, which is offices and apartments. All this is floating. And it's floating on the basement. So you live in the floating part. That's your plus room down there inside the pontoon at a kind of half story below the water. And then the other 2 layers of the building are available to you for living space also, along with the roof deck.
And you have a built-in swimming pool too, right?
And you can go swim. People have boats at their units. This was actually designed as a middle and low-income unit development, so this was not a high-cost, high-end luxury development, and so far it's worked very well. When you actually go to visit it, it's covered in, every railing is covered in bikes, so it's like barnacles of bikes everywhere. Question in the back?
How much of a current there is like in that actual pond? How much stress is there on the actual infrastructure there?
From the currents?
Yeah.
There isn't much in the way of currents. This is called the IJsselmeer, and it used to be an estuary like the San Francisco Bay, or maybe more like the Chesapeake Bay, and they dammed it in the 1920s with the Afsluitdijk, and that turned this into a freshwater lake, a huge freshwater lake, which they now use to recirculate water for drinking water. So there's not a lot of current in this space, in this particular part. So let me close with a thought about what it is we might try in the Bay Area. And we have different concerns than the Dutch. While the New York Times has recently discovered the Dutch and often has articles lauding the Dutch and all of the things that they do, there are limits, and they don't address biodiversity. They also don't work a lot on water quality, surface water quality. That goes down to the ocean or to rivers. And they've dammed most of their rivers. So when someone says, let's do what the Dutch do, think about those possibilities. Lose your native species, contaminate your water with a lot of nitrogen, high concentrations of nitrogen, dam all your surface rivers. That's not the part we want to emulate. So what we might do would be something, and I'm going to joke a little bit about it, but we might do something where we think about the dig hole, make mound strategy, which is the oldest strategy in landscape architecture, a classic. I've saved you all a graduate education in landscape architecture. Dig hole, make mound, and balance the amount that you dig with the amount that you pile up. Wisdom of the ages. And what we're talking about is digging on the land side, piling up, and then building a big habitat wedge out to the bay so that that wetland is there to support us in terms of ecosystem services. This low but wide, wider than in this drawing, levee would provide protection from waves, and then we can live with a higher water table on the backside and sell housing to people. Also provide housing for people who can't afford market rates. And my students have been making models of this to try to explain to the public. Arturo here is pouring water into his model to show how these buildings would float. People have a lot of skepticism about floating. It's very interesting. It's an old idea, very basic physical formulas, and yet people have skepticism, so it's good to demonstrate. We were involved in a competition. My school at Berkeley, College of Environmental Design, was on a professional team, joined a professional team to explore options for adaptation in the Bay Area, and we used this idea, what eventually we called tidal cities, where this is a road, this is a big wetland, these are ponds off to the side, and tide gates on these ponds and inflow from tributaries allow the pond to take in the highest tide, and then like you're breathing in, but then when you're breathing out, you only let it go out 2 feet because you don't want to strand all these floating structures in a muddy pond. That would not sell. So the idea is to take the tide in through tide gates and then hold it except for a 2-foot exchange and keep circulating water from higher elevations through tributaries through that pond, kind of a honeycomb strategy of ponds. And then this last slide shows something of what that might be like to live on decking attached to floating units that are 3-4 stories high, and then have other units with conventional foundations adjacent that could go higher to 20 stories or more on deep foundations that are appropriate for a seismic region. Another thing the Dutch don't have to cope with is liquefaction risk. So we have to design for biodiversity, we have to design for equity. We have a much more unequal society economically than they do, and we have to design for a seismic risk and an under-maintained infrastructure context. So we're imagining doing this now in places like East Oakland around the Coliseum. Easiest to do, where there's a redo of a big urban parcel like the Coliseum site itself. And the neighborhoods around it don't want to be this yet. They think this looks like tech workers' housing. And that's mostly low-income Latino and African-American communities. And they would like to find ways to stay in place longer. So we're right now doing a study I can't show you pictures of yet that tests the idea of using shallow canals to wick water out of the neighborhoods of deep East Oakland and hopefully allow people to stay in conventional housing for longer. But that's an example. We could do something like this in San Rafael. We could do it in Foster City. We could do it in Palo Alto, East Palo Alto. So I'll leave it at that and open up for questions. I'm sure you have a lot to ask me about. Thank you.